Hello, everybody. My name is Álvaro Coutinho, and I'll be presenting for you the paper Advances in the Simulation of Turbidity Currents. The team that helped me doing this work is listed below, and we are all from Brazil. You will also note that I changed a bit the title of my presentation, and you will understand why during the presentation itself. Okay. Well, the contents are, I will go through the motivation, which are turbidity currents, how to model turbidity currents. I'll show you some example computation, and I will briefly talk about emerging paradigms like UQ and machine learning, and I will end with some conclusions and discussion. Well, our motivation here, you can see in this picture, basically a sketch of how the oil reservoirs in Santos Basin in Brazil are represented. You can see here, if you follow my mouse here, the pre-salt regions where you can find evaporites, and in the post-salt you can find the turbidites, which are rocks formed by deposition of sediment carrying organic material. You can see this in current present-day seismic images. And turbidites, they are very important in the exploration in oil and gas. Those are the basic, where you can find most of the of oil in Brazil. And yeah, as we'll see, the formation of reservoir by turbidites or even by evaporites, as I should say, is a complex multi-physics and multi-scale process. It involves compute and data intensive. It is compute and data intensive with huge workloads. And the current trend is to incorporate the UQ and predictive data science. Well, just for you to see, in this picture, you can see in the left the reconstruction of the 1929 giant turbidity current deposits. It was basically in the west coast of Canada. You see that in SECT, you can see the detail of the sediments carried by let's say 200 or hundreds of kilometers at the velocity, which basically around 20 meters by seconds. And you see this marvelous and complex fingering, which represents the different deposits over the years. In the right, you can see some simulations that we did for simulating experiments done by Petrobras back in 2017 that more or less mimic in lab what we find in nature. The main interest here for the oil industry is to understand the process from where from where comes the sediments that you see today, in the sense that if there is a good prospect in one side, if you find in another finger like this, the same sediments, there's a good chance that there might be a good reservoir, oil reservoir in that region as well. Just so, it just adds to the comprehension of the complex geological nature that in decision that people do in the oil and gas industry. Well, models for turbidity current simulations, they range for basically 3 types. Simplified models, depth average based on the shallow water equations, and depth resolver, where we can range for even the direct numerical simulation of Navier-Stokes or the standard Reynolds average Navier-Stokes, and what we do, which is large edge simulations. On the right, you see that I will focus my presentation today in the shallow water equations and the LES depth resolved simulations of turbidity currents. Well, Let's now focus on the shallow water models. And equation 1, you can see, the shallow water model written as a system of advective diffusion equations. But U is a vector of the node, the water head. U and V are velocities. Qx and Qy are the fluxes. The tensor A are given below. The diffusivity is basically the ratio between viscosity and density. S is the source term, and G and G prime. G are the model of the gravitational acceleration. G prime is the reduced gravity due to buoyancy, and the other coefficients you can see in the slides. The tails are the paper below. So we discretize the system shallow water equations using DO2, which is a library, finite element library that incorporates many things that makes this a very nice environment for developing algorithms. And we do use a flux correct transport of basically a finite element flux corrected transport. There's 7 steps here. This is basically the steps we do for flux correction for the FCT algorithm. Again, the details in our paper below, but we not only implement the shallow water model FCT. If you see the paper, there are contributions in the prelimiting the fluxes, in the time step and the low order solution, but I don't have time to go into the details of the FCT algorithm today. What is more of our interest here is coupling the shallow water equation with a sedimentation. Basically, we are looking for coupling this to mimic the stratigraphy sequence. I mean, the history of deposition of sediment deposition in this area. So we're looking for stacking patterns in sequence stratigraphy, which are conditioned by the available accommodation space and sediment inflow rate. In turbidity currents, we are trying to mimic and simulate the Buma sequence, and this progression of events producing this progressional pattern, like you see in the right, retrogradational, aggradational, and progressional. And the bulbs are created by the events merged in the progression. So we try to reproduce the overall stacking pattern on a larger scale rather than intricate structure of bulbs and lobe channels. This can only be simulated by a full 3D simulation, as we're gonna see later. So we are coupling our shallow water code with a code, a stratigraphic code from Petrobras that is described in the reference below. Now we're gonna see you a example of application of this technology. We're gonna simulate the sedimentation of a regular bed. This is a real life problem from turbidity currents arising from the canyon in Brazil called the Almirante Câmara Canyon. We're gonna be simulating several events. We have the inflow data, the total volume, and we're gonna do 3 sedimental sub-steps. So we're gonna have 6 simulation steps for the stratigraphic application. In the first 4 steps, we do 1 event and supply this amount of sediment volume. And 50 and 60 steps, we have 2 and 4 more events with this amount of sediments. You're going to see in the slide, almost 2,300 mega cubic meter per events of sediments. This picture here, you see the final deposit for 6 different granular types of sediments: coarse sand, medium sand, fine sand, silt, and clay. And you can see the deposit's thickness in the scales are in meters for all these granularities. And how this compare with the real life. So you can see on the deposit formation in the right and top right. And the trends in the top figures are characteristics of Buma sequence observed in nature. And in the well, in here in the left below in this picture, you can see the point of injection, the bathymetry, and the area is about 140 kilometers by 100 kilometers with a height of 2 kilometers, basically a shallow water system. And in the right below, we see the deposit techniques, superimposing with what was really observed by Petrobras in 2004 and has been published in Portuguese and in internal report. So we see a pretty good agreement in our simulation. It is multi-scale coupling of stratigraphy and a shallow water flow simulating a turbidite current. Now, let's come back to and discuss a bit what are the challenges in depth resolved turbidity current simulations. First of all, is turbulence with a multi-scale phenomena, and Reynolds number found in natures of order are of order of 10 to the power 9. Then the second challenge is usually we have several granulometries. Basically, this is a multi-phase flow, but we usually assume that the Boson-esque hypothesis holds. And then we have to cope with deposition and erosion, which is basically mass transfer between bed and suspended flow, entrainment, and bed topological changes. And different flow regimes, we observe that the moderate to high sediment concentration flow is basically a non-Newtonian, and we'll see this in an example in a few moments. The depth resolved model is basically given by the arbitrary Lagrangian Eulerian formulation of the compressible Navier-Stokes equation. U again are the velocity now in 3D. P is the pressure, rate stands for the Reynolds numbers, and EG is a unit vector pointing to the direction of gravity. C are the different concentrations for the different granulometry. We assume that the standard is compressibility equation, and U tilde is basically the velocity minus the mesh velocity, which is typical for AO formulations. And this is coupled with a polydispersive mixed equation for sediment transfer for each one of the different granulometries. And then we have a US is the settling velocity for each of the granulometry. The details of the formulation is in our IJNMF paper, you can see below. Further, we have to cope with the bed load flux, where it's given by equation 5. This is the QBL is bed load flux, and the CR is a reference concentration. Sigma stands for the packing fraction of the settled sediments, and the bottom velocity of the bottom boundary is given by the Exner-Pauli equation, and this integral operation reflects the position thickness along time. Well, we can simulate this with our in-house software called Edge CFD, which is a multi-physics parallel code. It has an edge-based data structure. It's hybrid parallel. It can do MPI open and pure both. It supports to a standard stabilizer formulation or residual-based VMS for variation of multi-scale formulation for the compressible flow, and stabilized formulation plus shock capture for transport and compressible flow. It has some features like adaptive time step control, our solver of choice is in exact Newton, and we can do, of course, AO. There's this paper that you can find the more details about parallelization, and the description of our flow solver is a very recent, was published last year in the International Journal for Computational Fluid Dynamics. We also use a lot LibMesh, which is basically a framework for finite element analysis. It's open source, and every time we would like to explore, adaptive mesh refinement courses, use LibMesh, which support, HP and HP adaptivity. And we also did integration with the libmesh and Paraview Catalyst to do in situ visualization. So basically, the workflow for the Turbidity current simulation for the fully resolved, the 3D formulation, you generate the mesh, you initialize, and then you start the time step loop. If need, you can steer the simulation by a reset simulation parameters in runtime. Using that box, where we can see DF Analyzer, which is our data analysis tool. Then we solve for the flow using the variation of scale method. It has conversion. We proceed to the sediment solver, which is also VMS. If it is adaptive mesh refiner, we do apply AMR algorithm as refinement in course. We compute the sediment deposition, and then we compute the mesh movements. Every time we are annotating in the database for possibly steering the simulation data like number of cells, element type, etc. Data for the nonlinear solver, nonlinear tolerance, residual linear tolerance, specific what kind of solver parameters we are using. And then we are also annotating the database data for the adaptive mesh refinement course, like error fraction, global tolerance, error estimator. And also we use the adapter, the Paraview Catalyst, to provide in situ visualization and also metadata like data extraction for solution snapshots. And we also annotate the time step. So if needed, we can query in the provenance database and come back to the solver, to all the solver, and changing all these parameters in runtime. Well, let's see an example. This is a 3D sedimentation deposition with a real bed bathymetry, as you see in the top figure. The more red colors and more heated colors represent the more bigger depth. This is a real, real bathymetry in the northeast of Brazil, and you can see the sediment concentration in the picture below, generated by in situ visualization. Here, in this, you are basically simulating a tank, which is a non-dimensional 14 by 12 by 2, which is basically a typical of experiments with real bathymetry. We are simulating actually a lab experiment via real bathymetry at a grass shaft number 10 to the power 6 is a turbulent flow, Reynolds 2000. And with that settling velocity, you can see basically a 5.7 to the power -3. This order, you can read the boundary conditions, and you're exploring in situ visualization in data extraction. In this table here, you can see, a computational cost for all this and the elapsed time for the different stages: the flow solver, the sediment solver, the in situ visualization plus data extraction, the reading and writing, and collecting provenance data for our steering the simulation. And you can see below the storage requirements in raw data for the only data that we are, store, the raw data for provenance data extraction and in situ vis. Well, it's basically telling you that we're spending most of our time in the flow and sedimentation solver, and by using in situ visualization, we just store point PNG files. Your storage area is very, very, very much diminishing, decreases a lot, and we don't pay a lot as well in either in CPU time and data extraction in order to be able to in order to steer our simulation. A more interesting example is when we do parameter online tracking and fine tuning. We were doing the simulation, and as you can see, I mean, the turbidity currently is progressing with adaptive mesh refinement. In the graph, you can see the number of elements a long time. And at a certain point, we decided, taking a look in the flow, in the nonlinear tolerance, that we can relax a bit. So in order to have, keeping the same accuracy with less elements, and then we do this intervention in runtime, and because this was a long time a simulation. You can see that before we adjust the simulation in runtime, the average solver time by iterations is almost 4 minutes, and we cut this by almost 1/2. And we have a mesh with adaptive mesh with hexahedra, basically, with about 2.4 to the power 10 to the power 6 element. We reduced this by 1/3. And we took 17 days to complete. And if we do nothing in this intervention, it was expected almost 1 month simulation in more than 400 cores in our supercomputer. Well, coming back, as I said before in the introduction, sometimes when we have more dense concentrations, we have to take into account that the flow is basically non-Newtonian, and currently you have this rheology model for dense granular flow introduced by Job et al. In Nature in 2006. You can see the reference below by Job, Forter, and Polucan. That basically says that your apparent viscosity now depends not only on the pressure, but on the shear rate, and the viscosity depends on this I, which is the inertial number, which is basically the ratio of inertial time scale TD to the macroscopic deformation. This is a very interesting way. And then now we use this to simulate dense granular flow of a rigid obstacle. We are basically simulating the experiments and by Moriguchi, which also presents an numerical simulation. Basically, we release amount of dense sediments that go down until it hits a wall, and we measure the impact force on the obstacle for different slope and friction angles. In the simulations, we're going to see provided by Moriguchi. They used the Bingham-Morcullen model, and we did some parameter fitting to obtain the parameter for the mu-I rheology. You can see the density for the light fluids and the density for the dense granular flow, and the viscosities you have a contrast of almost 10 to the power 8 between the viscosities of both fluids. And after we consider an angle of for the Morcullen about 35 degrees, and those are the parameters we obtain by fitting the mu rheology to the BMC model. We can see this in the animation and the adaptive mesh refinement, and the sediments hitting the wall. And you can see in the bottom below several simulations, including the physical experiments there, and including, we can see the physical experiment by Moriguchi simulation, our simulation with the Bingham-Morcullen and the mu rheology, and a new simulation using a space-time framework did by Gezenhuis and Burr in Merrick Burr, which is have been recently published in IJ and MF. We can see that our simulations produces a very good, reproduces very well the time for impact, but there's some discrepancy on the magnitude of the impact force. But anyhow, this is considered a very good result. It's changing gear now. Well, as you see, and there's when also when we have a viscosity which is dependent of concentration, and there is a lot of closure relationships available. This table, you can see that different authors and different functional form of this dependence of the viscosity from the concentration. This is basically, try to reproduce different lab experiments. In the chart on the right, we plot several curves, and the gray area is an adjustment we see that can fit several of those closure equations. So we use we basically do a model discrepancy for adjusting this, and for this case, the Reynolds number is also turbulent, about 1.5 to the power 10, 10 to the power 4. And this is, can see a picture of the current. And this, we are seeing the average of deposition computed by our workflow engine using stochastic Galerkin SC with 257 samples, and you see, in red the average deposition and two standard deviation above and below for this solution. And with this, we can do Bayesian calibration and prediction. We have selected 16 points, while the green points will be the validation point, and the red one, the calibration point for the depositions. And we do AMC, Markov chain Monte Carlo with more than 100,000 samples with a 50% burn-in. And we basically gave us more than 100,000 samples for AMC integration. You have on the right the probability characterization of model discrepancy by the scatter plot of the hyperparameters that we are taking into consideration. And in the figure below in the left, you can see the predictive mean and confidence interval deposition along the center line compared to the observation, which is very good results. And with this, we can, all this calibration, we can extrapolate and then predict a deposition for a different situation, considering the injection, the inlet mixture velocity at 0.75 instead of 1. And then we run again, and by using this Bayesian calibration prediction, we arrive at the PDFs you see in the charts for points P13 and P16, comparing them with the observation, and we see that we have a pretty good agreement for P13, but not so good for P16. As emerging fields, we are seeing the use of data-driven models to let's say to extract spatial temporal structures from this, and for this we use a dynamic mode decomposition, which is purely data-driven. We run a high fidelity simulation. It is a turbidity current with a Grashof number 2000 with a very fine mesh, and collected 3,000 snapshots. And we use this to in DMD theory, where the nonlinear dynamics are mapped to use a linear infinite dimensional operator. And then we provide a low rank approximation, this is A tilde, well, and the Frobenius norm of the error for ranks for 50 to 250. You can see a reasonable error, and speed ups from ranging from 500 to almost 200 in compared to the forward simulation. And you can see that quantities of interest like mass conservation and the front position are very well represented by very low rank solutions, which is it's a promising way of doing more uncertain quantification and parameter exploration in this type of problems. Another emergent field is what we call hidden fluid mechanics. So here we use a neural network where we impose the satisfaction of a PDE and this loss here that we measure concentration and we have some measure of concentration, some data, and some observation, and also with we use this to let's say extrapolate the other fields we don't know, like velocity and pressure. And this well, you can see in the graph below in the predicted by the neural network, the PIN, what to say, the physics informed neural network, and the ground truth, which is for the simulations. In the batch size is 3,000. We do this as a 6-hour running on a laptop with a standard GPU, and you can see for this is for this time step you're seeing the velocity sitting along the height of the domain. You see a pretty good match between the prediction by the neural network and what we consider truth here. The truth is, which is basically by synthetic data. Well, to close, we see that high fidelity simulation of natural and man-made processes challenges. We see that there's a lot of physics interacting multiple scales, have a large match, which gives us high computational costs, huge data, etc. And we have the ambition to reproduce engineering artifacts and processes found in nature. We see that multi-fidelity models are necessary given the quantities of interest we see in practice. And we touch in new emerging paradigms, UQ, predictive data science and machine learning. All of this, HPC, machine learning, and data science are here to stay. We need all of them to produce, a meaningful simulation nowadays. And I close with acknowledgements of our supporting agencies. And I'm happy to show you this movie here. And while you see this movie, I will be here to entertain any questions you might have. Okay. Thank you very much for your attention.